Hi, I'm Bradley Rothenberg, CEO and founder of nTopology, and I'm here to talk about engineering design. Engineering design flips around the term that we normally use, which is design engineering. Engineering design is actually the engineering requirements driving the design. So at nTopology, our mission is to enable engineering teams to design the most transformative products, just like this Cobra Aero engine, which we'll kind of touch on a little bit later in the presentation. But first, why is this important today? Manufacturing has gone through the most important transformation of the last 40 years. This is the shift to digital manufacturing. But the issue is the current design software, the current engineering software was designed and engineered in the 80s for drafting. And that's a blocker, that's a bottleneck. Engineering design is really not possible on top of 80s technology, right? Like you need to represent any shape, you need to have physics driving the design process, and also massive automation is needed to explore the full design space really, really quickly. Especially because this new manufacturing methods, they really open up what's possible. They allow you to make any shape, they allow you to design and control exactly where material is, etc. And so today, it's legacy design software that's the bottleneck in advanced manufacturing. And that's where nTop comes in. So what makes nTop better? There's really three things: Unbreakable Geometry, FieldDriven Design, and Reusable workflows. Unbreakable Geometry. Why should you care about Unbreakable Geometry? So what? Unbreakable Geometry means that engineers can now run designs of experiments on thousands of iterations with zero model failures ever. Geometry never failing, this allows you to explore the entire design space. Normally when you're setting up a big design of experiments, half the time the model is breaking on the results. With Unbreakable Geometry, again, you can explore the entire design space, thousands of iterations, zero geometry failures. And these designs of experiments, they could be run in nTop, or they could be run from external tools like Mode Frontier, Process Composer, or even custom MDO software, like this example that Cognitive Design Systems did in partnership with Yamaichi Special Steel in Japan. They developed their own AI-driven design software with manufacturing cost calculations built using nTop. And they were able to explore hundreds of thousands of iterations on these simple bracket designs very, very quickly and rapidly to get to the best design that was cost optimal. And now today, with moving our geometry valuations over to the GPU, engineers can now make changes to complex parts with real-time feedback. And so what this allows, it allows smarter decisions to be made much, much quicker, much faster in real time. You're not paying engineers to watch a progress bar spin for minutes or hours a day. You're not paying them to redo work because a geometry operation failed or crashed. Half the time, engineers, they could be sitting at their computer, making changes to the model, and then just waiting for that model to update. Maybe they'll go get a coffee, maybe they'll take a break, and then they'll come back, and maybe there's a 50% chance of the model succeeding or not. That's wasted time. That's time that could be spent focused on engineering. So we got it, fast modeling, right? Big question is, how does this connect to the rest of our engineering process? And this is where field-driven design comes in. And so there's something really, really special and really unique about our new modeling technology, which we've talked about several times. There's a lot of information on our website about it. But what's really unique and really special is the way you can vary any of the design parameters spatially throughout the part. And this is because our underlying mathematical equations give us a field. So compared to the legacy boundary representation, in a legacy BREP, you only understand points along the surface. Our underlying mathematical implicit model, this gives us the ability to understand every single point in space. And so what this means is material can be controlled in a very, very specific, exact, and easy way. And so we're calling this changing of parameters or spatially varying changes field-driven design. And so what this allows for is, again, material can be defined and controlled highly specifically and very easily through 3D space. You can't do this in a legacy BREP. You can put the material where you want it as you need it in a very easy way. And so, okay, that's a little bit abstract, mathematical. What does this mean for engineering and manufacturing, right? What it means is performance-driven design. You could drive the design with actual physics. Throughout the entire space of material, we can actually store and interpret more information than just the geometry itself. Fields, they're the natural language of physics, whether it's temperature, whether it's stress, whether it's fluid flow. These are all fields, right? Temperature changes in space, stress changes throughout a part when you're bending it. Fluid flow could be really fast in some areas. If you look at a river, right, it's fast and slow in certain areas, turbulent in other areas. Fields are the language of physics. And so be it material, thermal, simulation, or empirical data, these fields can actually drive the geometry to produce, inspect, and validate the object for manufacturing processes downstream. This data allows engineers, design engineers, simulation engineers, manufacturing engineers to all communicate and collaborate within the same lightweight data set. So again, back to this Cobra Aero example. In the Cobra Aero engine, there were fields for pressure, for thermal, for aerodynamics, and for slicing and manufacturing, all combined together to synthesize, to create the actual engine block, which is the most critical component of the engine. It's where, the cylinder moves up and down. Data can come from any source to process geometry and then be exported to multiple sources simultaneously. And when we mean any source, we literally mean any source. That could be the fluid flow paths, right? Here's an example of, a manifold where you have 3 outputs and 1 input, but you want to maintain constant pressure. In this case, we're taking the fluid flow path results directly from Fluent, from ANSYS, and optimizing these flow paths so that we have the same pressure on all of the outputs. This is an iterative process, right? nTop is run, spits out a mesh that goes into ANSYS. It's run, creates a new, flow field. That flow field is brought back into nTop. The geometry is generated around that, meshed output again until it converges and all the inlets and all the outlets have the same pressure. So digital twin, no problem, right? nTop automatically provides for all of your downstream processes while also updating an existing PLM. For example, this heat exchanger designed in nTop using simulation feedback from ANSYS, there were several outputs. 1, a volume mesh. Volume mesh was sent into Fluent for simulation. 2, slices. Slices were output to EOS for manufacturing 3D printing. 3, surface mesh. Surface mesh was sent to Synopsys for as-built validation. 4, a BREP. BREP was output back into CAD for integration with the bigger assembly. And then 5, an nTop file. The nTop file and any other associated files were stored in PLM for data storage and audit and any updating and change requirements. Because inevitably, there's going to be changes. Maybe it's the inlet locations, maybe it's the outlet locations, maybe it's the number of inlets, maybe it's the number of outputs. And when those changes happen, you don't have to redo the work. They're just input into nTop like a computer program and regenerated. And so the field in nTop, it allows all of your input and export data along with the corresponding geometry to be stored in the same underlying function. And that data can flow through multiple sources, right? Not just nTop. It can flow into ANSYS, it can flow into Synopsys tools for validation. And so now reusable workflows. So what? Everyone has to learn a new piece of software? Well, yes, but kind of no, right? Yes, in that we do have a new modeling technology. We have a new system for interacting with that modeling technology, which is the block system, which is very powerful because you're creating your own blocks, you're creating your own functions. But also kind of no. What's amazing is an expert user of nTop can produce these really easy to use workflows and blocks so that others who don't know the software could just input the inputs and run it and start to learn the software and onboard onto it. And so what this allows is, as an organization, your expert users can create work that everybody across the organization can use. So you can innovate and stay ahead of the competition that's using yesterday's tools. And so these reusable workflows allows anyone else to reuse and easily get into the platform and start getting valuable work done. Really good example of this is the Stratasys jigs and fixtures, right? In Stratasys jigs and fixtures, the expert users at Stratasys, they created a workflow that automatically can create a jig for even the most complex parts. Something like a topology optimized bracket, something that looks like crazy geometry where the manufacturing engineer will be like, how on earth can I ever fixture this properly? Stratasys are experts. Their engineers are spending, some of their application engineers are spending almost the entire day creating jigs and fixtures. And they know how to do this best, better than anybody at nTop, and better than a lot of their customers also. And so what they were able to do was actually package that expertise into a very easy and simple to use set of nTop blocks that any user of nTopology can get and access and use and input the requirements to pass in their part and generate the jig and fixture. Additionally, their experts expanded and extended that workflow to also create a new set of workflows for masking. With the masking module that was just released recently, the masking module allows any CAD part to come into nTop, and with a few clicks, any engineer or anybody out there can say, let's mask this surface, let's plug this hole, let's tape up this surface, let's plug these holes. And there's a few parameters to control, the tapering and all of the other stuff that you'd want to control. And so once an engineering problem is solved, it can be reused in other similar applications if the requirement changes. And, the geometry changes without any manual effort. And so again, expensive engineering hours, they're not spent doing repetitive tasks. You're spending your time iterating, optimizing, and engineering to efficiently define the highest performance system. That expertise can be fit within, a simulation engineer could build out the simulation methods for that bracket design, and that could interface with the design engineer who's actually adding all of the structure in terms of the brackets. And so what this means is once an engineering problem is solved in nTop, it can be reused in other similar applications. And if the requirements change, the geometry changes also without any manual effort or without a lot of manual effort, right? And so in nTopology, you're actually designing processes and the part is the result. The part is the output. And so, automation is well established in manufacturing. In nTop, we have design automation, engineering design. The engineering is driving the design. The design is the output. So another great example of design automation is Lightforce Orthodontics. They've built their entire design and engineering processes on top of nTop. And this process is kind of, incredible. What happens is, Lightforce Orthodontics is shipping a box with braces and orthodontic devices to dentists or orthodontists. Actually, my dad happens to be a dentist, but that's a side fact. They're shipping these braces to orthodontists, and the orthodontist gets a box in the mail, opens the box up. The box has a guide with the braces in them. They put it in the teeth, and then they put some glue on it, put it in the teeth, put the wire in, take the guide out, and now you have braces, and it saves time installing the orthodontic devices. But in order to design and create the actual, the things that go on your teeth, the guide and the wire guide and all the labels and all of the other stuff, they've built that on top of nTop. And what happens is a dentist or orthodontist scans the teeth, uploads that scan into a cloud server. That scan gets fed into nTop, and instantly, 15 versions of nTop get spun up on the cloud, or as many versions as there are teeth, and they're producing the actual orthodontic braces. Before nTop, they were doing this with the legacy tools manually. They had engineers actually going through every time a doctor would upload and creating these braces. And you can't ship thousands of orthodontic braces a day if you have to do it manually. And so again, this is nTop powering the next wave of manufacturing, the next wave of products into market. These expensive engineering hours, you're not spending them doing repetitive tasks. Instead, you're spending that time iterating and optimizing to efficiently define and design high-performance systems. And so we talked about unbreakable geometry. We talked about field-driven design. We talked about reusable workflows. And we talked about all of these fields combined into one format. And so what does this mean for future changes and requirements in manufacturing? If the requirements change, which they're going to, right? The concept design for an aircraft is constantly changing. A car is constantly changing. Does this mean you have to start from scratch? You have to rebuild it again? No, right? By bringing all these data elements together into this one 3D language of fields, essentially nTop is future-proofing your company's engineering processes against changes in requirements and manufacturing process down the line. We built nTop to scale with the future of manufacturing. When I started nTop, we made a very, very specific decision to go all in on advanced manufacturing. We don't want to hedge on top of legacy data models and just build functions and features on top of a BREP, which is not going to scale. We went all in on implicit modeling. And so, again, your time is not spent redesigning. There's a requirement change. Only the inputs need to be changed to modify the geometry, simulation, validation, and manufacturing outputs. And so again, as requirements and processes evolve, your engineering outputs do as well. You just change the inputs. It's almost like a software program, right? A software program, you could change the inputs and the program reruns and produces a part. When you're using nTop, you're essentially creating a software program that produces a design or a part. And that software program allows you to explore all versions of that part, the entire design space, to get to a higher performing part quicker. So we've explained why leading companies, engineers, and manufacturers are already adopting nTop. But what does this mean for the world at large, right? And so right now, we're entering a platform shift, right? We're facing all this pressure to increase the efficiency, to reduce emissions, to reverse environmental impact, and provide a sustainable future for the future generations. It's the platform shift from gas to electric, et cetera. At the same time, we're advancing and exploring deeper into space. We're exploring deeper underwater. We're exploring these spaces with private companies. This is unprecedented in history. Great example of this is Hollow AM. Hollow AM has built their entire design and manufacturing process on top of nTop to enable the most innovative and most high-performance chip heat exchangers out there. And no other software could provide them with the performance and reliability that nTop could. And this in turn, this value that they're producing is spreading out into their customer base, producing new, more innovative products and spreading through the industry, pushing this new wave forward, pushing these new technologies into market quicker with higher performance. Another example of innovative products coming to market, leveraging field-driven design, is Impressio, who won the largest grant for the NFL Helmet Challenge. And they're leveraging nTop to design these custom lattice structures for the liners of helmets, initially for the NFL, but they could be for other sports, right? Hockey helmets, biking, right? And so they're leveraging nTop to actually solve a major problem, which is concussions when you have hits to the head. And Impressio is using nTop to design these innovative lattice structures combined with a new material that they've developed for better energy absorption. We have aerospace applications, lightweighting, radiation mapping, the design of heat exchangers. We go into automotive, seat cushions, surface texturing, structural optimization and sound attenuation, medical device, spinal implants, surgical guides, prosthetics and orthotics, heavy machinery, oil and gas, right? Again, lightweighting is important here. Drilling guides, injection molds, drill heads, burners, and then consumer goods, better cooling for CPU. Remember, all that excess heat, that's wasted energy. If you can create better cooling, you reduce the energy usage. Helmet liners, sports accessories, footwear, bicycle parts, cell phone parts. To learn more about nTopology, our mission, and our software, visit ntopology.com. And on there, download a trial, get into the software, open up an example file, change the parameters, see if there's an application that makes sense for you. And if there's not, reach out to us, get in touch with us, because we could help your team outperform their engineering requirements at unprecedented speed and efficiency. Thank you very much.